Welcome back to conceptual physics today. I'm just going to do the kind of the final notes on this chapter. Okay, so just kind of a little bit of a review here for you. We've been talking about projectiles, right? Projectile motion. So projectile is anything that is flying through the air and is only affected by the force of gravity and air resistance at the most. So just a little review. You know, there's a lot of projectiles being flying around lately. Baseballs, basketballs, footballs, all projectiles. Okay, so just let's see if you remember this. So, you know, let's just say that we have a ball here that's being dropped. It has an initial x velocity of 0, and then we have a ball that's being shot with an initial x velocity of 10. Remember, x is the horizontal, y is the vertical. So the question is, which one hits the ground first? Yeah, you're right. This is a bad picture because this one shot at 10 should be at the same level. So just imagine that the one that shot at 10 is at the same level as the one that's going to be dropped straight down. Which one hits the ground first? That's exactly right, Landon. Thank you very much. Neither of them hit the ground first. So the one that is shot out here has a different projectile path than the one that falls straight down. But the time is the same for both of them because they're both going the same distance in the horizontal direction, and they both start out with 0 velocity. So the velocity in the y direction is 0 for both of them. So that's to remind you that no matter what's going on in the x, it doesn't affect what's going on in the y. So a ball that's dropped and a ball that's pushed out at 10 meters per second, as long as they start at the same level, they fall and hit the ground at the same time. Okay, so another thing that you have to remember is this. Let's just say that you kick a ball, which we did with our foot, right? And it's going at 30 meters per second, right? So this is review also. So when you kick a ball at 30 meters per second and it goes up, Cole, and when it comes back down, what, if it's on the same level here, what's the speed of the ball at that level? Very good, Luke. It's actually 30 meters per second. So yeah, it's the same speed. It is a different velocity because it's in a different angle, but just remember, everything on the way up is the same as everything on the way down, as long as there's no air friction. So the speed at one level is going to be that same speed later if it's at the same height. Very good. Yeah. So just another thing to remember. Here's your initial velocity, right? And you got your x piece of the velocity. Alvin, how does that x piece look when you're right here? How does the x part? So that's your x part of your velocity. Your y is up. How does your x velocity look when the ball's at this position? It's the same. Very good. Because the velocity in the x direction, unless there's air resistance, it's constant at all parts of this projectile motion. So up here, the velocity is only x. The actual whole velocity of the ball is the slowest here, but that's not because the x is any slower, because it's the same. It's because there's no y. So there's little y here, big y here, no y here. Then here you're gonna have the same x again and a little y. So your velocity increases, but the x part is constant. Okay, and then one last the kind of like review question here. So let's just say that we kick a ball at, let's say it's at 70 degrees, goes pretty stinking high, comes back down, right? And we'll say that the velocity is 20 meters per second. The question is, what if we kick that same ball at still 20 meters per second, but instead of 70, this time the angle is 20 degrees? What do you know about that? Yes, it's going to land in... right in that spot right there, exactly the same, right? Because 20 degrees plus 70 degrees equals 90 degrees. So as long as you have the same speed, if you have complementary angles, which means they add up to 90, then they'll land in the same spot. The trajectory looks different, but the big difference is, you know, the one that's at 20 degrees has a bigger x, and then the one that's at 70 degrees has a smaller x. So it has more time in the air to go in the smaller x velocity, so it ends up going the same as a larger x velocity with less time. Okay, so for the new stuff here. So this is where we're getting into the two-dimensional motion. This is where people start to whine and complain a little bit about the math, but it's really not that hard. Just keep in mind, each one of these things you have to do 2 math problems in order to get the one answer. So the question here is, how far away does this ball land? So I have x here because x is just a variable, but in this case it is the x displacement from the edge of the cliff. So just so you know, we got to first find how much time this thing is in the air, because we know it's going 5 meters per second in the x velocity, right? So if it goes 1 second, this would be 5, right? If it goes 2, it would be 10, 3 would be 15. Any questions about that? Okay, so I'm going to show you first how to figure out the time that it takes for this thing to fall 10 meters. Now keep in mind, it has nothing to do with this velocity in the x direction because it's completely independent. So I'm going to just say this is how I find time, okay? And so you can use this formula. Okay, so the time that something falls, if the velocity in the y direction is equal to 0, it's equal to the square root of 2x, and this x is this height here, okay? So x is used for a lot of different things. So this height is this x in this formula, okay? So 2 times the height divided by little g, and that's how much time it takes anything to fall if, so this is if, the initial y velocity is equal to 0. So in other words, you're just dropping something, like we did off that stairwell. Yeah. Yeah. So the math looks like this. 2 times 10, because keep in mind, x is just the height that something's being dropped from. 2 times 10 divided by little g, which it could be 10 or negative 10. If it's negative 10, then this would be negative here too. So at this point, it doesn't matter that much. But the time that takes to fall then is the square root of 2, which happens to be, thank you very much, Kaylee, 1.414 seconds. Now, let me tell you, when you do this math, you should leave like that many decimal points until the end. So always do that. Leave like, 4 numbers at least until you get to your final answer, okay? So 1.41 seconds, that's how much time you got in the air. So I'm going to take that and I'm going to jot that down here, because that's not the answer. That's just what I had to do to figure out the answer. So the time that it gets to be in the air is 1.414 seconds. Okay, so now I can figure out how far it goes. Okay, so I figured out my time, and now I know that my velocity is equal to my displacement over time, and x is what we're looking for here, right? Yep. So how do I solve for x or get it by itself? What do you guys say? First, multiply by t.
Both sides.
Both sides, yep. So TV equals x. Okay, so it used to be when I taught physics, like, a long time ago, I'd say x out the TV and then get your homework done. But people don't even hardly watch TV anymore, do they? Oh, okay. So, Okay, the time is 1.414. And the velocity in the x is 5. So the distance that I fall away from the cliff is, yes, very good, Kaylee, 7.07 meters, right? Okay, so when very good, Kaylee, thank you so much. When I ask you to put your number into the computer program for the quiz and the check for understanding on this, you put 7.07. I don't want you to put the labels. Okay, just put the numbers. Okay, so that's the end of our lesson for this week. I'll have an example or a quiz up there to check for your understanding. Let me know if you have any questions.